DeBroglie's equation. This is really an extension of that whole idea from the duality of light, that light is both a wave and a particle. Well, DeBroglie extended it. He said, if waves are particles, then particles are also waves. So not only looking down at the tiny, tiny, smallest packet of energy, photons, he was looking at every single particle, that when I walk, I actually oscillate. I move as a wave. A train on the tracks moves in a wave. The earth rotating around the sun moves as a wave. It oscillates. And this was the formula that he came up with. So we've got lambda wavelength equals Planck's constant h divided by mass times velocity. Now this formula has one really, really important aspect to it. It's the units. I mean, of course, units are always the most important. Let me show you a huge takeaway from this. Let's write down all of the units. We've got lambda, wavelength is in meters. Planck's constant is joule times second divided by mass. Okay, I'm going to tell you right now, mass has to be in kilograms. You've got to put that in kilograms. And the velocity is meters per second. Okay, now looking at this, you're like, whoa, how do you get meters out of all those units? It's actually right here, buried in the joule. A joule is kilogram times meter squared divided by second squared. That's when you break apart. Joules is a derived unit of the mass, time, and length. If I take that and substitute it in here, let's see what we get. Okay, so the joule is a kilogram times meter squared divided by second squared. Let's see what happens when we start canceling. So a second will cancel with this second. That second will cancel with this second. Kilogram cancels with kilogram. 1 meter cancels with that meter, and you have meter equals meter. So be really careful. Make sure you always have the mass in kilograms. Now, another really big takeaway from this, you can look at the formula itself to find the takeaway. Notice that mass is in the denominator. So the larger the mass, the smaller the wavelength. So big takeaway from this. The larger the mass, the smaller the wave. So if we're looking at an electron, tiny, tiny mass, just the opposite would be true. Small mass, considerably large wave. So electrons, small mass, are going to have a sizable wavelength. Me, wow, huge mass in comparison. My wave is so small that when I walk, you can't see me oscillate. Planet Earth, huge mass. We can't visibly see it oscillate. Now we can calculate the wavelength, but it is going to be super, super small. Now I saw an AP question and it gave a list of different options and it said which particle has the smallest wavelength. Easy. Smallest wavelength just means biggest mass. And on the question, it was a planet. A planet would have the biggest mass, therefore the smallest wavelength. So big takeaway, the larger the mass, the smaller the wavelength. And that's why when we see something large moving, we don't see it oscillate. Is there a wave? You bet there's a wave, but it's just really, really small. So there is DeBroglie's equation.